This lesson will prepare you for the acid-base and acid-base equilibria unit in AP Chemistry. We will review topics such as the definitions of acids and bases, the strength of acids and bases, and the pH formulas. There will be some things that are review from grade 11, and there will also be some new topics that are specific to the AP course. The first thing that we'll do is discuss the definitions of acids and bases. And there are three definitions of acids and bases, each becoming more and more broad in their ability to help us understand acids and bases. Although we have three, each have their own specific uses as well. The first definition of an acid and base is the Arrhenius definition. By Arrhenius, an acid is a substance that dissociates to produce H+ ions in solution. And the way that you can recognize an Arrhenius acid is by the hydrogen at the beginning of the formula. So for example, hydrochloric acid is a classic Arrhenius acid. When it dissociates in water, it produces H+ and Cl-. Bases, by Arrhenius definition, dissociate to produce hydroxide ions in solution. And you can recognize an Arrhenius base with the ionic formula composed of a metal and a hydroxide ion. So sodium hydroxide fits this definition well, as it dissociates in water to produce sodium ions and hydroxide ions. Now it's important to note that it's the H+ and the OH-, or the hydrogen and the hydroxide ions, that are responsible for the properties of these substances. Properties such as acids react with metals to produce hydrogen, acids react with litmus to produce a red color, or they're clear in phenolphthalein. Bases, on the other hand, react with litmus to produce blue, or react with phenolphthalein to produce a pink color. By Arrhenius' definition, the acid-base reaction is a simple one, where an acid plus a base produces a salt and water. And it's important to note here that the salt is not just sodium chloride, it's any salt or an ionic compound that can be produced here. The Bronsted-Lowry definition of an acid and base is a bit broader, and it covers some of the flaws in the Arrhenius definition. One of the flaws from the Arrhenius definition is that H+ ions don't actually exist on their own in water. They exist as H3O+. So you'll see from the Bronsted-Lowry definition that we see H+ in our reactions rather than H3O+. The other flaw with the Arrhenius definition that is corrected with the Bronsted-Lowry definition being broader is that there were some bases or substances that had the properties of bases that didn't reflect the definition very well. So we'll look at an example in a moment. The Bronsted-Lowry definition of an acid and base involves protons. And when we look at a proton in chemistry, what we're talking about is an H+ ion. What you can remember is that hydrogen has one proton and one electron. So when it becomes H+, what we're left with is a bare proton in solution. So that's why we call H+ a proton. Now, by this definition, an acid is a substance that donates a proton, and a base is something that accepts a proton. When we look at these substances and their reactions in water, what we need to do is look at the substance. So in this example here, we're looking at vinegar, and we're adding water. These reactions are always going to be equilibrium reactions, which we'll discuss further as we go along. Now you can recognize a Bronsted-Lowry acid as one that usually has this Cu group at the end. So you'll remember from grade 11 organic chemistry, this is the carboxylic acid group. And it's this hydrogen at the end that's the acidic proton. If we were to draw a picture of this molecule, we've got CH3 and then COO H. The hydrogens that are attached to the carbon are not acidic, okay, so they will not be donated. But this hydrogen here is acidic. It's able to be donated to the water molecule. The reason for that, okay, is related to the structure here. These oxygen atoms are more electronegative. They pull the electron density away from the hydrogen, weakening this bond and allowing it to be broken. So what we have here is we've got this hydrogen being donated to this water molecule. And so the vinegar molecule is losing a proton, so we're taking away an H+. We're left with a negative acetate ion. And the water molecule, I'm adding H+, and we're left with H3O+. A Bronsted base is a substance that accepts a proton. Ammonia, NH3, is a classic and the most basic of the Bronsted bases. So it's really important that you know the formula for ammonia, which is NH3. Now most Bronsted bases, structurally, what you'll find is that they have nitrogen in them. They're sometimes referred to as nitrogen bases. The reason that they're able to accept a proton structurally is because they've got this lone pair of electrons on the nitrogen. So what you'll see is that the formulas will usually have carbon and hydrogen in them, but they'll often have nitrogen as well. And what you'll see is that whenever the proton is being accepted by the base, it's always being accepted at the nitrogen. So the hydrogen comes in here, okay, and these are actually the electrons that are used to form the bond. So what happens here is that the water is the donor in this situation. It's donating a proton to the ammonia, and we're left with the ammonium ion and hydroxide. Now this is an example of one of the bases that didn't fit the Arrhenius definition of a base. Although ammonia had basic properties, so it would turn phenolphthalein pink, for example, the formula didn't fit the definition. And it was impossible for chemists to see how this substance, when in water, dissociated to produce hydroxide ions. But as you can see from this broader definition, we do see that hydroxide ion present in the solution that is really responsible for the properties. Now you may be wondering why water in this situation is accepting a hydrogen ion, and in this situation it's the donor. This is what is called an amphoteric substance. So water has the ability to act as an acid or as a base, and it will change depending on what other substances are present. So in the case of reacting with vinegar, because the vinegar is more acidic, the water is forced to act as a base. While in the second example, the water is the more acidic of the two, so it's the one that donates the proton. Other examples of amphoteric substances are common polyatomic ions. So as you can see, this HSO4-, it has a hydrogen for donation, so it would be able to donate this. And it's also an ion and would be able to accept a proton to become H2SO4. So this is what an amphoteric substance is. Now these two reactions are both examples of acid-base reactions using the Bronsted-Lowry definition. They both involve the donation of a proton from one species to another. And that's what the definition is under the Bronsted-Lowry definitions of acids and bases. Now the third definition of an acid and base is the most broad definition. And this one is new to you. This definition, the Lewis definition of an acid and base, defines an acid as a substance that can accept a pair of electrons, and a base as a substance that can donate a pair of electrons. So in this case, when we look at the ammonium interacting with water, it is still a base by this definition, but how it is defined is a little bit different. So what is happening here is this pair of electrons is actually being donated to form this bond with the hydrogen, and that's how we form the NH4+. This pair of electrons is what makes the hydroxide actually negative. So by the Lewis definition, the NH3 is still a base, but when we look at why it's called a base, it's because it's the one that's donating a pair of electrons in this reaction. This example here with boron trifluoride and ammonia is another classic example of a Lewis acid-base reaction. You may recall from grade 11 that boron, when we draw its Lewis structure, is often left electron deficient. So this is a stable molecule. There's no double bonds. It's just got 3 single bonds to the fluorine. So when we look at this, it's actually sp2 hybridized. Because it's trigonal planar, it's sp2 hybridized. And what we end up having left over is an unhybridized p orbital. So essentially boron has an empty p orbital. That empty p orbital is available for accepting a pair of electrons. So when it reacts with the ammonia, the pair of electrons from the lone pair in ammonia are actually donated. So the ammonia is acting as the base, as the donor, and the boron trifluoride is accepting, so it's acting as the acid. And this is the molecule that we have left. Now when we look at complex ion formation, which we've discussed already, it involves a metal ion and one of the common ligands. So in your notes you'll see the common ligands there, the ammonia, the cyanide, the thiocyanate, and the hydroxide. These also involve a Lewis acid-base interaction. So what's happening is the ligands are the donors of the electrons, and the metals, being electron deficient, hold these empty d orbitals. And those d orbitals are the location for accepting the lone pairs of electrons. Now for these, you don't really need to know structurally what's going on, and you would never be asked to draw an energy diagram to show where the electrons are going in. That's much more advanced. But what you do need to be able to do is to write reactions from word equations to recognize when a complex ion is going to be formed and to be able to generally get the formula correct. So these are a couple of examples, and then there's a few more examples in your notes for you to try. So if we look at this one, it says concentrated ammonia solution is added in excess to a solution of silver nitrate. So there's a few key words that are always used when we are identifying that there is a complex ion going to be formed. So if you've got concentrated solution or you've got an excess of some kind of solution, okay, and that solution fits one of the ligands, so in this case ammonia is one of the common ligands, and you've got a transition metal. Those are the clues to tell you that you are dealing with a complex ion reaction. So here we've got silver nitrate. Silver's common ion is Ag+. It's its only ion is Ag+, and we're reacting it with the ammonia, so it's important that you know the formula for ammonia is NH3. Now, as a general rule, we've said this before, the number of ligands that will attach is double the charge. So in this case, 2 ammonia molecules will adhere to the silver ion. So what we're left with is a complex ion composed of silver and 2 ammonia molecules. Remember, the transition metal is in the center and the ligands are loosely attached. The overall charge of this is still positive because the ammonia has no charge. If you were to follow the general rule and look at this example here of excess potassium thiocyanate being added to a solution of iron 3 chloride, what we would have is the Fe3+ being the transition metal. It's important that you recognize that potassium here is a spectator ion, and you know that because it's not one of the ligands, okay? And you've been kind of given the clue using the word excess that this is going to be a complex ion formation. If we use the rule of double the charge, that would suggest that we get 6 thiocyanate ions attached to the transition metal. And when we look at the overall charge here, we've got to consider the fact that the iron brings +3 and the thiocyanate ions bring -6, so the overall charge here is -3. This last example, we've got excess sodium hydroxide, hydroxide being one of the common ligands, added to a solution of aluminum chloride. Aluminum chloride does form complex ions, and its ion is 3+. Now you'll notice here that I'm not using the general double the charge rule. This is a specific complex ion, okay, that is loved by the writers of the AP exam. So this is a common complex ion formation that you could potentially see. So it's important that you recognize this one. When you've got aluminum and hydroxide, okay, there are going to be 4 hydroxide ions attached. The overall charge of this is -1 because of the 3+ and the -4. So what you're going to want to do is practice the questions that are in the notes, and we will take those up. Now, in the Bronsted-Lowry definition, which is going to be the main definition that we use in this course, when you write the reaction for a substance in water and have the proton transfer, you're going to be able to identify what are called the conjugate acid-base pairs. Or if you're given just a regular acid or a base, you could also identify its conjugate. The definition of a conjugate acid-base pair is a pair of 2 substances that differ by 1 proton. One of the substances is the acid, and one of the substances is the base of the pair. And the way that you identify it is by which one has the proton to donate and which one would accept a proton. So if we look at this reaction, this is the vinegar molecule again, just written a different way, and this is the acidic proton. This is the proton that's being donated to the water. This acid molecule differs by 1 proton from the acetate ion on this side. So they are an acid-base pair. And they are related to one another by 1 proton. This is the acid in the pair because it has the extra proton, and this is the base in the pair. Water and the hydronium ion are also an acid-base pair. They differ by 1 proton. In this case, the water is the base, and the H3O+ or the hydronium ion is the acid. Now you might wonder why we would even consider this. You're going to see that these reactions are all equilibrium reactions. So there's a forward process and there's a reverse process. In the forward process, the vinegar molecule is acting as the acid and the water molecule is acting as the base. And in the reverse process, the hydronium is the acid and the acetate is the base. So that's why we have them labeled on both sides of the equation. Now, when you first study water in high school, you're told that if you've got pure water that's distilled, there are no ions in the solution. When you've got regular tap water, it's got all the ions, like there's metal ions and other things in the actual water. In actual fact, when we've got a sample of water, there is actually a very low concentration of hydrogen and hydroxide ions. And this is because water molecules, being amphoteric, have the ability to both accept and donate protons. And when water molecules interact with one another, they produce the H3O plus and hydroxide ions in the solution. I'll do a demo for you next class that'll show you that in actual fact there are ions in the solution. Now this is an equilibrium reaction, and it's got an equilibrium constant associated with it. It's called Kw, the equilibrium constant for the dissociation of water. So the W stands for water. As you know, when we want to write the equilibrium law, it's the concentration of the products divided by the concentration of the reactants. Water being a pure liquid is not going to be included in the equilibrium law. So this equilibrium constant is H3O plus times hydroxide ions. And this equilibrium constant has a value of 1 times 10 to the negative 14, which is very, very small. So even though at first when you're studying water, you learn that there aren't any ions in solution, the reason that we discussed it in that way is because the concentration of the ions is tiny when we're talking about neutral water. The concentration of each of these ions is 10 to the minus 7, which is very, very small. When we look at a solution, it's important to identify whether it's a neutral, acidic, or basic solution. And it's neutral, as you know, if the amount of hydrogen ions is equal to the amount of hydroxide ions. In an acidic solution, the amount of hydrogen ions in the solution is greater than the hydroxide. And in a basic solution, the hydroxide ions are in a higher concentration. Now, this is it's important to note that this is the way that you should be viewing acid, base, and neutral solutions. Sometimes when students are first learning about acid-base chemistry, they think of acids as being substances where there's only H3O plus and bases where there's substances where there's only hydroxide ions. But the reality is all solutions in water have hydroxide and hydronium ions in solution. It's the relative concentrations in that solution that decide whether it's an acid or a base. So if you've got something that's really basic, like very high on the pH scale, the concentration of this is going to be very high, and that's going to force the concentration of the hydronium ion to be very, very small, okay? Because these always multiply to 1 times 10 to the negative 14. And that brings us to the pH scale. And as you know, low on the pH scale are the acids. Above 7 on the pH scale are the bases. And we're dealing with a neutral solution when we are at a pH of 7. Okay? And that makes sense because when you're at a pH of 7, the hydrogen ion concentrations are equal to the hydroxide ion concentrations. And so when we look at the Kw being 1 times 10 to the negative 14, that would mean that if it's neutral, each of the H3O plus and hydroxide will equal 1 times 10 to the negative 7. Okay? And we'll review this a little bit later, but the pH is the negative log. And so if you take the negative log of 1 times 10 to the negative 7, you get a pH of 7. This Kw being temperature dependent at 25 degrees Celsius aligns with the pH being 7 at 25 degrees Celsius. So technically speaking, as the temperature changes, the Kw will change, and therefore the pH of neutral might slightly modify. Okay? It's a very, very small difference. So generally speaking, this pH scale is fine to use. The next very important topic in studying acids and bases is to understand the difference between a strong acid or strong base and a weak acid or weak base. And this understanding is really going to control how we approach many of our calculations. I've already asked you to memorize these strong acids and bases. This is key to being able to do many of the calculations that are coming up, is to know and be confident in your knowledge of the strong acids and bases. By definition, a strong acid is something that dissociates completely. So when we're dealing with strong acids and bases, we're dealing with complete arrows. And these really fit the Arrhenius definition of acids and bases. So these are the strong acids, and anytime you're dealing with one of these acids, this is how they will behave when they are in water. They simply dissociate completely to produce H plus and the counter ion. The strong bases also dissociate completely. They are salts formed with the metals from what I refer to as the big little b on the periodic table, and hydroxide ions, and those dissociate completely. So this is a visual here. Okay, if we start with this amount of hydrochloric acid molecules at equilibrium, or once we've allowed it to complete its reaction, we will have the exact same amount of H plus and Cl minus. So the molecules will be fully dissociated in the solution. When we're dealing with a weak acid or base, we're going to need to use the Bronsted-Lowry definition because we're going to be looking at equilibrium. A weak acid or a weak base is something that only partially dissociates in water. And you're going to see that a lot of these will dissociate less than 5%. So the way that you can recognize them is that they've got the Cu group, so organic acids tend to be weak acids. Okay? And hydrogen fluoride is another weak acid. It's not on the list. Okay? We'll discuss structurally why some acids are stronger than others. These are going to have equilibrium constants associated with them, and they'll have a small Ka value because the equilibrium does not go very far to the right. Weak bases are those organic bases that I discussed earlier. So you'll see they've got some carbon and hydrogen, okay, and then they've got the nitrogen in them, and the nitrogen is where there's a lone pair that accepts the proton. Now the key here is to understand that when you've got a weak acid or base, it doesn't dissociate completely. So when you look at the before and after, say I had 100 molecules of hydrogen fluoride to begin with, I might only dissociate 5 of those. So if it was a 5% dissociation, I would only dissociate 5 of them. The other 95 molecules would stay intact. So when you look in the solution, there's fewer H3O plus ions in the solution, okay, which is going to affect things like the pH. This table here shows you the relative strength of the acids and bases. So our strong acids are up here, okay, and as we move away, something like ammonia is a very weak acid. So it's very unlikely to donate a proton. What we've got on the opposite side are the conjugate bases. So this is the perchloric acid, and this is the perchlorate ion, and these are related, connected by one proton. So this is the acid and this is the conjugate base. Now when you're looking at a conjugate acid-base pair, the stronger an acid is, the weaker its conjugate will be as a base. So the more likely this is to donate a proton, the less likely this is going to accept a proton. And that makes sense because the farther the reaction goes towards the products, the less likely the reverse process is going to be able to happen. We'll study that concept quantitatively a little bit later on. What we will do now, though, is talk about the structural implications of a substance and how you can look at the structure of a substance and decide the relative strength. So when you want to compare two molecules to one another and decide which one is a stronger acid, you've got two things that you need to look at. You need to look at the strength of the bond that needs to be broken. The stronger the bond, the weaker the acid will be because the bond needs to break in order for the proton to be donated. The other thing to consider is to consider the polarity of the bond that needs to be broken. So the more polar a bond is, the stronger the acid. The reason for that is, as you'll see in the case of having oxygen present, okay, the oxygen is drawing the electron density away, okay, and allowing for the hydrogen to be donated more easily. So we've got a few different kinds of acids. We've got hydrophilic acids, which are ones that don't contain oxygen. So we call them like HX acids. They've got H, the hydrogen ion, and then they've got X, which is a halogen. When we're comparing these, we want to look at the comparative bond energy. The HF molecule holds the strongest bond because the fluorine is the smallest of the atoms in this group. The closer the hydrogen and the fluorine can get to one another, the stronger the bond is going to be between the two. So as we go down this group, the bond to hydrogen gets weaker and weaker, and therefore the acid gets stronger and stronger. Okay, so HI is the strongest of those acids. And the HF bond is significantly strong, okay, so it's a significantly weak acid, hence the double less than symbols here. Oxoacids are acids that contain hydrogen. And we've got a couple ways that we can compare them. So we can compare oxoacids that have different central atoms but have the same number of oxygens. So HClO3, HBrO3, and HiO3. And in this case, what's going to happen is that the strength is going to increase with the electronegativity. So as we go up this group, the atom becomes more and more electronegative. And what that is going to do is draw the electron density away from the bond holding onto the hydrogen. Okay, so if we look at this molecule here, okay, we can see that this is what the structure is. So the chlorine is in the middle, there's the three oxygens, and then the hydrogen is attached to the oxygen. The more electronegative this chlorine atom is, the more it's drawing electron density away, and what the impact is a weakening of this bond, which makes it stronger. Now, if you've got the same central atom and a different number of oxygens, so we've got this list here of HClO4, HClO3, ClO2, and ClO, the rule is that the more oxygen there is, the stronger the acid. And this, again, is related to drawing electron density away from this OH bond that needs to be broken for the substance to act as an acid. The more oxygens, the more electron density is being pulled away, and the weaker this bond becomes, and it's more acidic. If you look back at the list of strong acids, HNO3, H2SO4, HClO4, those are all the molecules that are holding the maximum number of oxygens with those central atoms. The last thing that we're going to do is review the pH formulas that you learned from last year, and we'll do a few examples, just basic examples, using the formulas, and then ones where we're dealing with strong acids and bases. So this is your acid-base chemistry toolbox, I'll call it. It holds all of the key formulas that you need to be comfortable with. It's all based on this pH formula, right, and this relationship here from Kw. So they can all be derived from those two formulas. And if you need a review of that, you're welcome to come and see me. So pH is the negative log of the concentration of the H3O plus ions in the solution. Now it's important to note that chemists, although H3O plus is the more appropriate way to report this ion, if it's reported as H plus, that's fine as well. So pH is the negative log of H3O plus. Rearranging that formula, we get that the concentration of H3O plus is 10 to the negative pH. The P, recall, stands for the power. Okay, so in this case, the POH is the power of the hydroxide ion. So it's the negative log of the hydroxide ion in the solution. The hydroxide ion concentration is therefore 10 to the negative POH. The POH and the pH of a particular solution always add up to 14. Remember that no matter whether the solution's an acid or base, there is going to be some hydroxide and some hydrogen ions in the solution. And their pHs will add to 14. Their individual concentrations will always multiply to 1 times 10 to the negative 14. Let's look at a few examples here. The pH of rainwater collected in a certain region of the northeastern United States on a particular day was 4.82. What is the H plus ion concentration of the rainwater? Okay, if you look to the toolbox, we're looking for the hydrogen ion concentration. So the formula is simply 10 to the minus pH. So H plus, in this is the case, you could write H3O plus or H plus, both are accepted. And it's 10 to the minus pH, and it's equal to 1.5 times 10 to the negative 5. Okay, we have to remember to include our units of moles per liter. For significant digits, when you're dealing with pH, the number of significant digits in a pH is actually the number of decimal places. The 4 in here is actually just the placeholder. It's telling us what the power is, okay? And then the other ones are actually the measured values. So in this case, there are 2 significant digits, so I reported 1.5 times 10 to the negative 5. The second example, the hydroxide ion concentration of a blood sample is 2.5 times 10 to the negative 7. What is the pH of the blood? Okay. There are a few approaches you could take. You could use the Kw to find the H plus and then find the pH, or you could find the POH first by taking the negative log of the hydroxide concentration, okay, it being 6.60, and the pH is simply 14 minus that, which is 7.40. So in terms of significant digits, there are 2 significant digits in this number, so there are 2 decimal places in the POH. By subtraction, there are 2 decimal places in the pH. As a general rule, if you always keep 2 decimal places, you'll be fine with the POH. Now we're going to spend much of our time doing calculations in this unit of looking at pH of various solutions and looking at the pH after acids and bases have reacted with one another and examining titrations in great detail. What we can do at this stage with our knowledge from grade 11 and our basic use of the pH formulas is actually study solutions of strong acids and bases. Okay, because as you know, a strong acid or base is a substance where the reaction goes to completion. So there's no equilibrium. When you're dealing with an acid like HCl, which is a strong acid, it breaks up into H plus and Cl minus completely. So if I know the concentration of my HCl, I'll know the concentration of my H plus in the solution, and I'll be able to determine the pH. Okay, the same is the case for bases that dissociate. With bases, we do need to be very careful of the stoichiometry and look at the formulas to help us with that. We'll see an example of momentarily. So in this first example, the concentration of an HNO3 solution is 0.0125. What is the pH of this solution? When you're dealing with problems in acid-base chemistry, you always want to first identify what type of solution you're using. So you need to identify this is a strong acid. Okay, because it's a strong acid, it dissociates completely. So that's the reaction, and we can see that in a 1-to-1 ratio, the concentration of the H plus is therefore 0.0125. Okay, there are essentially no HNO3 molecules in this solution. Now that I know the H plus, I can use my pH formula and take the negative log of the concentration, and I get a pH of 1.90. In the second example, it's asking for the pH of a sodium hydroxide solution. So first thing is to recognize that it's a strong base and know that it dissociates completely to produce sodium ions and hydroxide ions. Because of that, the concentration of the hydroxide in this solution is the same as the original concentration. They're in a 1-to-1 ratio. Now that I know the hydroxide ion concentration, I can find the pOH, which is 1.37. And then by taking that away from 14, I can find the pH of 12.63. In this third example, we've got barium hydroxide. Barium is a member of our big little B, so we know that this dissociates completely, so I get barium 2+. Okay? And in this case, I get 2 hydroxide ions. So although the concentration of the barium hydroxide is 0.0425, when it dissociates, the amount of hydroxide in the solution is actually double. So in this case, the concentration of the hydroxide ions is 0.085. Now that I know the concentration of the hydroxide, I can simply calculate the pOH and the pH, which is 12.93. So that completes our introductory review lesson of acid-base chemistry.